is titled Acids and Bases, and we've spent a lot of time talking about acids. So let's look at bases. Strong bases completely ionize. And we get metal ions and hydroxide ions. And sodium hydroxide and potassium hydroxide are the most commonly used ones. Weak bases do not dissociate completely. And most Bronsted-Lowry bases are weak bases. We can write a Kb for these, just like a Ka, just like an equilibrium constant expression. So we have the dissociated form, the two ions on top, and the whole thing on the bottom. So we've got sodium hydroxide right there. And let's look down here at potassium hydroxide. The Kb would be K plus times OH minus over KOH. However, those are both strong, so we wouldn't really need a Kb for those. We need a Kb for weak. Now NH3. NH3 isn't a metal and hydroxide. So we need its dissociation equation, how it reacts with water. NH3 plus H2O. NH3 is a base. We know that because we're in the base section. So a base accepts a hydrogen. Therefore, water is the acid, so it donated. So we have NH4 plus on top with OH minus, and on the bottom, NH3, because water is a pure liquid, not included. Now, we can use that fact to find the Ka for the conjugate acid of a weak base. So NH3 is a weak base. So its conjugate acid is the NH4 plus. This Kb we would find in a chart, and then we could determine Ka. Now, if we have a strong base, then the OH minus concentration is equal to the concentration of the whole base. And then we could find the POH and then the pH by subtracting from 14. If we have a weak base, we have an equilibrium problem.